Okay, hello guys. Привет, Катя. So today we'll continue Spaces and Times number 5, and today we'll talk about waves and superposition. We'll talk what is it. So waves, it's a very important thing in physics, because if you remember, particles and waves are actually the same according to quantum mechanics, and it's a very paradoxical thing. So we should talk about this a lot in different aspects, but you started something. But first of all, I'll ask how was the things with the previous tasks, questions, whatever. Huh?
Well, we didn't have time to do them this time around. The first time when we didn't have time, but I honestly, I looked at them and I do not know how to approach them.
Yeah.
Like, what is going to happen if we start counting from a different place? I don't honestly don't know how to approach that.
You don't know how to approach. The first was in the process of count
Yes.
zeros. Well, does that process can start also from all zeros? But you said that you understand these questions at the beginning, so you don't know how to solve them, or what?
I said the opposite. I said I did not understand them at all. I was lost during the last lecture.
Okay. So, maybe we can recall where exactly you've been lost. Guys, can you tell me when you? The best way, by the way, the best way when you're lost, you just say to me right away while the lecture is going. Ask the question or whatever. This is the best. If you get lost, just there's no need to continue, right? So I'll ask you in the future, if you get lost at a certain point, just interrupt me and ask, and we'll continue after explaining this, something like this.
We just don't understand the questions. I think that's what Papa trying to say.
That too.
Say it again. What?
Papa, I don't think Papa understands the questions. I understood the lecture, but Papa, I don't think we don't really understand the questions.
So it's about the questions mostly. Okay, let's then talk about the questions again. And the first, my writing is very bad in this, so a process of count. Yeah, because I'm not writing the whole thing, right? That's why
Oh yeah, yeah. No,
I'm
no.
just writing some parts of it. Okay.
No, I agree.
So can you maybe read the first question, Katya, or maybe Antosha, because
What
you
happens if we start counting?
come closer to microphone because I cannot hear you. That's that.
You need to go maybe to the computer.
What would happen if we start counting from different
Vacation.
locations?
You get
What will happen with what?
What would happen if you start counting from different locations?
But what will happen with what?
That's the question. I don't know.
guys, when I ask you, you said you understand.
I told you.
You wrote it.
I have a diagram. It says here.
I cannot hear you guys.
We have a diagram. 0, 1, 2, 3, and 1 is also 0. 2 is also 0. 3 is also 0. So if we started from 1, what would happen? Could we keep counting from 1?
I don't have this diagram here. That's why that's my bad here.
Give us another chance. We'll take a look at it.
Okay. And the second is time is change and space is anti-change. Does this mean that all space is identical, unchanged? This is pretty clear. At least the question is clear. I'm not saying that it's clear, but
The question is the second one.
But the last one, last one. What if you change the particles? Like nothing should happen because they.
No, what's the answer on the second one first? If you know, if you understand the second, what's the answer? What do you think? It's the question. What do you think really? So the time is change, right? Universal change. This is actually time, right? And the space is in sort of way of anti-change. It's like quiet thing, right? Anti-change, something is not changing, right? Like with a preservation or something. Does this mean that all in space is identical and unchanged? What do you think?
Identical, no. Unchanged, yes. What do you think, guys? Because we have different things in space, but they don't change.
They don't change, but they change actually. But they change with time, right?
Time.
So it's another thing. So we see it in space, but it still has time, its own time, right? So it's changed. Yes. Okay, but what about identical? Is anything identical or not? Is there something identical in space?
Well, the particles are identical.
The particles are identical. Yes. So this.
Aren't identical.
But the planets are made out of particles. But the thing is, despite what Zeta said, the particles differentiate based on their location.
Yes, locations, actually speeds. There are certain things that differs.
Speed does not apply if there is no time.
Yeah, well, we talk about identity, right? Usually in physics, they say not about speed and coordinates, right? But the features of the particle. So the particle as it is, without their changes in speed or whatever, right? The particle is the same. The particles, if you compare them. But they can have different speeds, different orientation to each other, moving like this or that. So this is sort of like what is called external thing. You know, there are internal things, internal features of particles, and they are the same. And there are external things like coordinates and blah 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 blah. So we're talking about when we talk about identity, we're talking about internal things. So this particle, like this particle and that particle are totally the same, and the result of it, that if we exchange their positions, right, so we just exchange them, would something happen or not?
No.
And physics says not. No, nothing will change, except one interesting thing. There are certain particles which are called Fermi particles. When you exchange them, you have, remember you have to change the direction of time. The order, or let's say the order of all the particles, if you try to count them, order of all the particles in the universe, actually, the whole universe. So if you change just two, any of them, like one here and one in some other galaxy, they are totally identical, really. They're identical, but the only thing that will change, if we change the direction of time. Interesting enough, right?
What?
So yes. So it's the same thing. You know this expression, I already mentioned it, paradoxical expression, that all individuals are the same and that they are unique. Each person is unique, and that means that they are totally the same. They're all unique.
Oh yeah, actually that's true.
So they are unique. So they're different. Like look at difference to each other, but they are unique, and in this uniquity or whatever the name, they are the same. So the Fermi particles, there are two types of particles: Fermi particles and boson particles, Bose particles. And these Fermi particles are interesting. That they are unique, but they are identical, really identical. And their uniqueness is that you can exchange them, but this uniqueness cause the change of difference of time. So the order, you would say, that this is particle 1, this is particle 2. If you exchange, the order is changed, but the particles are still the same. So that kind of thing. It's interesting stuff. And Bose particles are totally identical. You exchange them, nothing change, just nothing. Bose particles are particles of so-called fields, force fields, like electromagnetic, nuclear fields, gravitational field, whatever field you have, whatever power field you have, or they say in physics, they say interaction, like electromagnetic interaction. So these fields or interactions, they are carried by the Bose particles. and the what we call matter, usually we call matter, because matter, fields are matter too, but what we call matter, like we can touch and everything like this, usually it is Fermi particles. There are protons, neutrons, and electrons mostly, but there are other particles too. But this is a little ahead, okay, so just mentioning this. Okay, the third question, what will happen if we exchange, an order of 2 steps in time? Can we do the same in space? Okay, I'll just explain. It's the same thing, like, because I spoke about Fermi particles and Bose particles, right? Bose particles are, you may say, they are particles of space. Like field is sort of a space expanded, power field expanded in space. So all the fields, power fields, are connected with somehow with the space. So if you exchange the positions in space, nothing will change. It's like Bose particles exchange. But if you change positions in time, the time will change direction, of course, right? 1 second, right? So you exchange second in the position of 1. This is the change of direction of time, right? That's understandable. So just something to understand, that Fermi particles are somehow connected. It's not somehow, it is actually really particles of time, if you say, like per se. And Bose particles are particles of space. They have a space character. And Fermi particles have like time character. That's like something like this. And with the first, you said that you will think about it, right? And then we'll talk later, okay? Just don't forget to mention it to me. Okay? Okay.
You do think about it so that you.
Yeah, I'll think about it, of course. Yes, because but unfortunately, I don't have any diagrams in my notes, so I can connect what's this. The question is just two words. Okay, so we'll talk about waves and superposition. Waves, you've seen a lot of waves, right? In the ocean, in the lakes, in the bathtub, right? Anywhere, right? But also you probably know that the sound that we talk, right? Sound are like air waves, right? You heard of this, right? And actually we are communicating through the wires and radio waves again. So radio waves, the current in our electrical conductors, right? Electrical lines, they are waves too. So lots and lots of different waves around us, right? Actually, we may say that any interaction, like I touch the table, right? Like I touch the table, I actually don't touch the real particles there. I mean, real particles of matter, or electrons, protons, or whatever. I do not touch them. The only thing I touch, and what I feel actually waves. And the waves are electromagnetic. So like photons. Photons are the quanta of electromagnetic waves. So when touching anything around, and not only touching, smelling, right? Seeing, even hearing, because hearing is that our ear touches the air, right? The atoms of air, molecules of air. And our ear, as our fingers, they do not touch directly the atoms or molecules. They touch only photons that actually connects us with these atoms and molecules. So our interaction with the world, like our personal interaction with the world, it goes only through electromagnetic waves, nothing else, nothing. Like chemistry in our body, it's totally electromagnetic. All these chemical formulas, chemical changes, processes and everything, they're all electromagnetic processes. There are electrons involved, but electrons, again, the electrons, they interact with anything around with electromagnetic waves. So just understand what's the meaning of electromagnetic waves. It's very, very important. Like when you go X-ray to the clinic, again, it's electromagnetic wave. So radio waves are electromagnetic waves, light is electromagnetic waves, the heat that we feel like coming close to the hot kettle, right, or iron, you feel the heat coming, right, from it, or from the fire. This is infrared radiation. It is, again, it's electromagnetic wave. The sun, when you get the thumb at the sun, this is ultraviolet electromagnetic wave. So electromagnetic waves are everywhere, and we actually interact with the whole universe, our own, with these electromagnetic waves. Just understand how important are those. So, but anyways, waves, you understand that waves goes like like this, right? Something like this. Usually this regular function, regular thing, it is formulated by a formula that's sine, right? Remember this? Sine, right? Pronounced.
Yeah.
So sine of something, like sine of, like sine x, right? When coordinate is like this, right? X, right? There are also other things periodical too, lots of periodical, non-periodical functions, but the main is this. And we talk first about this thing. First of all, okay, well, I'll put it more, you know, this is y, this is x, and this is sine, function of sine. It goes like this. This point, and then goes again, the same thing. This point, it's 2 pi. And this point is, do you know what point this is? This is pi. This is 0. And this is?
4 pi.
4 pi, yes.
That's the cloud.
Yeah. When this is when x is not x but just, let's say, t, like time, right? This period from 0 to 2 pi, it is called period of wave. It's usually denoted by t, capital T, period. It's understandable why period, right? Because it's periodical, right? So 2p is a period. Then again, the same thing. Then again, then again, then again. So, and if you take any point on this function, any point, like this one, right? And you shift it for 2p. You move it to 2p. Where do you think it would be? It would be here. So the same value. Something like point A, right? The peak of the wave, here and here. So two peaks are distinguished from another by the period. Again, t. 2 peaks.
I have a question.
Yeah.
Is period the amount of time between two identical setups for a system?
It's not system. It's just a function. We're talking about the wave.
Okay, so is period the time between two identical values for function?
Yeah, if it's periodical. This is the function, the sine. It is periodical function, right? So if it's periodical, yes, this is period between two the same values. So the same values like these values, or like from this value, right, to this value again, t. Here is t, and whatever. If you take this point, again, where the same value goes like this, the same value is here, and again this is again t. So if you shift periodical thing to by in time, like by period t, you will get the same value.
Oh,
and
another question.
Yeah.
Maybe so period is maybe the minimum time, because if you take 2t, you still get the same value.
Yes, that's correct. But 2t is a period too. You understand, right? You may get 2t, still the same thing. It's periodical by 2t too, by 3t too, periodical. Yes, you're right. That's you're right in that. That you know, strictly speaking, yes, t is a minimum period, right? Minimum. But 2t is period too, as a term. Just yes, this is minimum period of time. That's correct. Yeah.
Okay.
So minimum, yeah. That's a good point. Okay, now what else we have? When you have in t, it is period, right? If in the same wave is in x, so in space, right? Instead of t, we have this. This is called lambda. I don't know how to spell it in English. Something like this, I think. This is Greek letter, lambda.
So do I.
And b is not pronounced, lambda. Without y? Okay. So without y. So, and this is called wave length. This is the term. So we have now two terms: period, minimum, right, in time for the wave, periodical. And because the wave usually is periodical not only in time but also in space, you know, like wave in the ocean, right? The same period, right? So, and it's called this period in space, it is called wavelength. So the length of the wave. So if the wave is going like this, right, like here's the beach, right? And the wave is going like this, if you run there and measure the difference between two peaks of the waves, it will be wavelength.
Can I ask you another question?
And if you use the clock when the wave hit the ground, right, you'll get the period. Okay, the question.
So what would be the units for the period?
For the period, it's seconds or whatever, time units.
And for the wavelength?
And what if wavelength, space units? What are space units? Meters, kilometers, inches, whatever. It depends upon the wave. The wave can be short, maybe long. Long means like the wavelength is big. That's called, let's say, long. It's not like it's wide, but it's long in this way. It goes like this. Wavelength.
Okay.
Got it? Guys? You got it?
Yeah.
Okay, okay. Now, so this is, you should remember, period and wavelength, right? Now, there's also one very important thing in waves, x or t, whatever, the term here, it is called phase. Phase. And phase is, it means that where on this wave we are looking at. Like for example, we're looking, or some device may be registering at what position on the wave are we. And usually under position we mean only this interval, because only this interval of the period, right? From 0 to 2 pi, only this. So in this interval, we want to see where are we at a certain moment. Where are we actually? Where are we looking at? We can look at this position, or this position, or this, 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 from 0 to 2p, to 2 pi, right? And this particular position, like here, it is called phase. And usually it is denoted by another letter, it's phi. It's called phi. Like this.
5.
Oh, phi. Phi?
Yeah.
Okay, so phi. So like this position is phi1. This position may be phi2. And we call this phase in physics. It's very important because the function is as it is, it's periodical. So it's the same with this shift of 2 pi, right? So we need only to understand what is going on, only this interval, short interval from 0 to 2 pi. And because it's important, we call it phase. So phase. One of the points on the coordinate axis, x or t, and we call this phase. And the phase is usually, again, it's like maybe pi, 2 pi, or some fractions of pi. Like for example, phase is p divided by 2, half pi, right? Or p divided by 4, like 1/4 of a pi. Or maybe it's pi phase, or maybe 2 pi. And 2 pi is actually the same as 0, right? So this is the phase 0. So this is the phase 0 too, because it's the same thing. So you try to, to put it into your mind what phase is. Phase is the point in this interval from 0 to 2 pi. Or it may be from 2 pi to 4 pi, because it's the same thing, it's regular. So, and again, when we talk here is phase 0. Phi is 0 here, and here phi is 2 pi. So it's the same thing in each period. Got it? I think you got it. Because we'll need this. Oh yeah, one more term, and this is the the maximum value of periodical wave, it is called amplitude, like A. It is called amplitude.
Oh, yeah, question.
Yeah.
Units for phase.
Yeah.
What are they?
What is for?
Units for phase.
Pi. Fractions of pi. That's what I say. The units of phase are fractions of pi. Phase is very interesting term. So phase is maybe 0 or maybe 2 pi, whatever. Is it space or time or whatever else in any wave? But the only thing we have to have this should be periodical. So phase is having sense when we talk about periods. So when something is periodical, and then we can take one period and talk about phase in this period. And why it is important, we will see a little later. Okay, got this right? Now also what we have other terms which I really needed for the waves. Is frequency f, which is 1 divided by period. So if period in 1 second, the frequency is 1. And the units of frequencies is hertz or Hz.
We've done it.
And hertz means that one oscillation per second. Well, that's understandable from here. If you get t 1 second, right? So 1 divided by second will be 1 hertz, right? So if we have t 1 second, frequency is 1 hertz. If we have t half of a second, frequency will be t half of a second. Frequency?
How do you get frequency from t?
1 divided by t.
So if t is 1 half.
1 divided by 1 half, which is 1 times 2, which is 2. Frequency equals 2.
2 hertz, right?
2 hertz.
And like if t is like 2s, frequency is 1 half. So 1 half of hertz. Just so you got the idea of frequency, right? And they are all like closely connected. Now we have, this is frequency. Now we have another term which is we have this so-called angular frequency. It is 2pf. This is again Greek letter omega. You should remember this because it's very often it's used all the time, like omega 4. And this is called angular frequency. Angular frequency. Why angular? Because 2 pi is an angle, right? Remember? 2 pi is an angle, which means angle is when you turn it like total 360 degrees, the whole turn. So if you do like this, you just Господи, как-то умножить-то будет, Господи. Multiply frequency by 2p. It means that we are counting not just how many oscillation is done, but how many angles are turned, like this. So this is one oscillation, another oscillation. So because anything is 2p, 2 pi, right? Any oscillation is 2 pi, period. Remember this, 2 pi each time. So 1 2 pi, another 2 pi, so we have this important like things. They're very closely connected, just 2 pi, right? 2 pi coefficient. But the meaning a little different. This is amount of oscillation, so how many vibrations goes, like in it per second, right? And this is how many angle change per second. So 1 oscillation per second, it is 2 pi, 360 degrees. Like 2 oscillations per second is 4 pi per second. And the same thing. So this is called angular frequency. And the same thing is the another term. Like we have frequency or amount oscillations per second, we can count like amount of oscillations per space, not t, but space. So we divide not by period, but by wavelength. And you can compare this with the period later. Look at this. So you have this 1 divided by that, but we do not use this particular thing, but we use instead this multiplied by 2 pi. 2 pi divided by wavelength.
And what is K again? Sorry, what is it called?
This is K, just a sec. It is just I'm talking about this thing, right? And this is called actually the term is the wave number or wave vector, because usually it is a vector, so we may write it like this, but in this case it's wave number. So wave number, this is the term, or vector, because usually it is a vector in space. Remember, there are only one t, but there are x, y, and z. Remember in space, right? Is there? So it is maybe calculated. This lambda is calculated regarding some direction in space where the wave is going. So the wave is going this way, like wave is going this way, right? And we calculate. This is lambda. So we calculate this, and then we divide it, 2 pi divided by lambda. So it is the same as frequency, like angular frequency, but not in time, but in space. You may write it somewhere or remember that wave number is a frequency, but not in time, but in space. The same thing. It's a very important term. You got the idea, right?
Yeah.
So it's all about periods, because it's all periodical, maybe periodical in time, maybe periodical in space, and we have these things. So now we're coming to the main point. Now superposition. Superposition. What is it? Like you understand probably, it's like naturally. Then when we apply like two forces, like we have some stone, right? And somebody is pushing it. Like maybe Katya is pushing it, right? This stone. But stone is too big. So you need some help. You ask Vitya. Vitya comes and push it, right? There are two forces. Like two forces, like F1, or maybe F1 and F2, right? And you both applying two forces in the same direction. What will happen with these two forces? What would be the total force of you both? What do you think? Yeah.
Vita push with the force F1 and Vita pushes with the force F2 in this. Probably a good way. Maybe if we ask them if they push in the opposite direction, one pushes one direction, the other.
It's whatever. F is a vector, so you may push this direction or you may push different direction. Remember how vectors are. So what happens with the vectors?
What happens if you're on a train, the train is moving in this direction, and you're walking in that direction? What happens?
You go faster.
Yeah, but what do you do? What do you add with the vectors for velocity? The train is moving at 30 kilometers an hour, and you're moving in the same direction at 5 kilometers an hour. So what did you do?
I add as the train is going, like how fast I'm going.
What did you do? What do you call
No, mathematically what you do. What you do mathematically, you have two forces. Add, right. And if you have vectors, you use summarizing of the vectors, adding of the vectors. Remember this triangle? Maybe you remember, I hope. It's a very good thing to remember and to recall. So if you have like two vectors in different directions, you use vector addition, not just numbers. But if you're not vectors, you like plus. So the total force is plus, right? Plus thing. And if they are vectors, it's the same vectors. The same. It's F is. But anyway, so it is addition. When you have masses, you have like mass of Vita M1 or Katya M1, Vita M2. What will be your total mass? Plus, right? Remember? So they added here, and many other things. Speed, like your daddy just said, right? Speed. You are coming together. One speed, another speed is v1 plus v2, or velocity, right? And again, speed is a vector, so you may use this. This is the additional speed, or another way, it's actually a relativity principle. Remember this first Galileo relativity principle formulated in mathematics. So lots of adding here, there, and lots of adding in physics everywhere, not only in mathematics. Lots of adding. And the same thing happens, actually the adding, yeah, I should say that adding is not always correct. In many ways, adding doesn't work that good. But in this situation, many situations still it's okay. These situations are called linear. Maybe you may remember this term, that in linear situation, just term, we're not talking about this. In linear situation, the addition rule works very good, works fine. So we have this linear situation in many cases with waves. So what happens with waves? If you have one wave, not periodical, like any wave, whatever, wave going this way, and another wave going this way, they're going together. What will happen? What do you think? Huh? Yeah, they crash, but mathematically, what will happen? Okay, they coming, nothing happened, like now they are interacting somewhere like this, right? This is going this way, here it goes this way. What will happen? Like here, there's not yet this wave come at this point. This is a coordinate, x or L or t, whatever. They're coming this way. Here nothing happens. Here, this is called, amplitude, right? The value, amplitude, right? Here, what happens actually? Huh? Say again? Not twice. Here. They're the same size here and here, but they are different positions right now. But okay, we go like step by step. Each point we look at each point in time and space. Actually, what we do, and look at here. Here amplitude is like this, or value actually, not value. Amplitude is a maximum, right? Here's a value like this of, but sometimes they call amplitude here too. And this way it doesn't come here yet. It's almost zero. So amplitude still here intact. Now we take here. This is the maximum amplitude. And this is here the value of another wave, right? So what actually happens? The amplitudes of the waves are added, like in regular way. It's a linear process. Linear process. When you add. So the actual, you summarize here, and the actual position will be here, because this point added to this point. You understand? Now take this point.
I understand.
There are two waves here. One put on another. The value of this wave is this. The value of this wave is this. The value of this wave is this. Those two values are added. And this is called superposition. They are added. So you may call this A1, and this is like A2. And here we have A. Oh, sorry, this is mixed. And here we have A equal A1 plus A2. And here it's here somewhere. You got this? So to this amplitude added this part. because to this wave is added part of this wave, this point. We go point by point, point by point. We look at the wave as a total like phenomenon, but we use it. You use it by point by point. You got this or not? Think. So the waves are adding to each other. One wave is added to another.
Imagine this, Greta. So the one wave comes in, right? And now the other wave goes on top of it.
Yeah.
It's not the same level, it just goes on top.
Yeah, something like this.
So let's suppose that this is two waves. If they're in this position, this wave does not start from the bottom anymore, it starts from here. Or you can think of it as this wave starting from here.
It's like a one wave climbing on another. Like imagine this is a mountain, and this comes the wave, and these parts are already climbing here. Those parts are climbing to that wave. Something like this. You may imagine this way or other way, but mathematically it's just adding this amplitude to this amplitude, and this is just A1 plus A2. Here the same here is here, at this point. It is, they are the same at this point, right? You see here and here. You just add one to another. It will be somewhere like here. And the same thing is like here and everywhere. So the summer of this will be a wave like this. So when they come like here, the result wave will be like this. Because here it's added to here. This point, another point. From one wave and from another. From this wave, from another wave. They climb each other. And they have this position, this amplitude. So the waves, the idea is waves are summarizing. The amplitudes of waves are summarizing in each point. They're adding to each other. And this is called superposition or principle of superposition. Principle. And this principle is, again, it's linear. It's not always correct. Like gravitational waves, you may add them only when they are small. When they are big, they do not add to each other. That's some other laws. It's very complex. So, but in many cases, still, like regular waves, like radio waves, most of the radio waves, most of this audio waves, like our sound, lots of other waves are just summarizing. You just summarize them, and that's it. So we'll talk about this a lot. So just think about it, and I'll show you what happened, like in two cases, right? Like for example, you have one wave sine, right, like this, right, and another wave which is similar to that, going like that way or whatever, and it's like, but this is another way. I write it like this, right? Like two waves put to each other in one place, one space, one time. What will happen here? Like we're taking again from point by point. We take this point, the maximum amplitude, because it's two waves, it's doubled. It's here. Here, both are zero, right? The values are zero. Here. So they're still zero. So the total wave will be like this. Here, right? It's doubled amplitude. 2A. If this is A, this will be 2A. Because they are at the same amplitude. They are all almost the same. Here, this is minus A, right? And both of them summarizing, how much would it be? Peter?
You said it before, but it's in the opposite direction.
Opposite, they're a minus.
There's a minus to it.
Minus 2A, right. And wave so goes like this. And here again, zero. So these two waves are actually, and there it's the same because they're periodical, they'll do the same thing. So we'll have, by the sum of these two waves will be the same wave but the doubled amplitude. Going from 2A to minus 2A, like this. If you add another wave like this, what would it be? What do you think? Like 3 waves of this.
It's 3 times as big.
3 times, yeah, the same thing. So this is again exactly that superposition thing. Now let's, and yeah, you may understand that they are on the same. We say the both waves are at the same phase. So phase is 0 or phase difference. There's also phase. Is it Z or S? Phase, I think difference. It's called usually delta. Usually call this the difference. Delta usually means difference. This again, this is the delta is Greek number, Greek letter. So this is a phase difference. So they are at the same phase. Now we got something else. We have one wave like this, right? And another is like this. The same amplitude, but going like this. So it's opposite, right? When it goes to plus A, at the same time this goes to minus A. What will happen in this thing? In this position, there are 2 waves again, but opposite to each other. And again, we're going point by point. We're taking phase 0, and here is phase 2 pi, right? Again, we can talk only about one phase, only about phase from 0 to 2 pi, because all the same is periodical. It's all the same there. From 0 to 2 pi, here is 0, 0 one way, 0 another way, right? Here, again. This is 0, here's pi, right? But here again, they are the same value, both 0. So 0, 0 here, 0 here, and 0 here too. What about here? Here's plus A, here's minus A. Summarizing them, adding them, what will happen? You said 0. So here 0, here 0, here 0, there, again 0, right? What about another point? This point and that point. They're summarizing, what will be? Some other point. 0. So you look at this, you see it's totally symmetrical. So the whole thing, the whole period, the whole interval of phases, right? It will give you 0. So this is called, by the way, this is called negative superposition or negative interference. That's another term, interference. Interference usually means that the wave patterns are somehow adding each other, and the picture will have. So we have superposition, negative interference in this case. And let's look at the phases of each of these waves. This phase of this phase, we can tell that this phase is phi1 is 0 for the first wave. What about phase of another wave? What do you think? This is phi2. What do you think phase of this wave is?
So phase by how much? How many pies does it take to get all the way to the bottom?
So I would not like to overcomplicate. Okay, this case is considered that phi2 is called pi, or because this is the t, this is maybe t half of t, or in the space wavelength divided by t. So half of wavelength or half of period. So this is pi, of course, because the whole period is 2 pi. So this difference from this, you will think about it a little later. Just look at this. It differs from this by pi because it's you may look to this like shifted here or here. So p or minus pi, whatever. So you may shift one like this main wave, the first one, like this is phi1, right? You may shift it like here, and you will get this dotted wave by pi if you move this wave to pi. So, and this is called the phase difference between two, and phase difference is pi. in this case. So negative difference, it is the lambda divided by 2, t by 2, or pi. The phase difference is pi. And those two are the main cases when we're talking about waves and superposition. Because one, when the difference of phases are 0, they call positive superposition, not negative, but positive. That's simple to understand, right? Positive. Amplitudes doubled. Amplitudes double. And when you have the difference, phase difference pi, they totally destroy each other. It's called sometimes I call it destructive interference too, because they destroy each other, and they have totally zero. Interesting enough that you have two waves, very powerful maybe waves, right? They go in together the same direction with the big amplitudes. Amplitude maybe like mountain of Everest high, right? Huge waves. But another is so deep, again, Everest deep, like, right? Minus 9 kilometers. Plus 9, minus 9, right? So they add each other, plus and negative, and they destroy each other. You have zero. You have totally plain thing. No waves, no nothing. So two of such waves destroy each other totally. And this is very important. This is a very important actually thing. We're a little late, but I'll talk about one thing. I'm a little sorry, but we have it to understand and to solve the questions that I'll give to you. Okay? So any questions to this?
No.
Okay?
Well, this is all very well. I can ask you questions later. I know. I'll go over it.
So you said that they feel like okay.
There was one guy, the Dutch guy, so Netherlands, right, who lived in 17th century, and he was a famous physicist. His name was Christian Huygens. Christian Huygens. And he was interested in many things. He was a very talented guy. Like, for example, he in something like 1658, I think, he invented pendulum clock. You know what pendulum is?
Pendulum.
Oh,
Yeah.
yeah, I know it.
Pendulum is that thing which is moving like this in the clock, like 5 o'clock.
Pendulum. Huygens. Christian Huygens.
Yeah. So this is a very important thing in history, because it's a very powerful thing. It's interesting about pendulum that the vibration, the oscillation of pendulum are very stable in time, and they do not depend on the amplitude of this. So you can go like this or maybe like this, but it still be the same period. The time will be still the same, whatever you do. Like when you как там качели будут?
Swing.
Sway. When you play on sway, just remember that you're on the pendulum, actually, and the periods are still the same whatever you do. They just do not rotate like this, but the period is very close. So very good clock, and those clock they work until 1930. So 300 years. The 300 years they were okay, like for humanity, right? Only in 1930, 300 years later, they were changed to quartz clock, which is more precise. And in 1970 or something, they were changed to quantum clock.
But the quartz clock, they still use a pendulum. It's just
Yeah, they use pretty often in like a wristwatch or whatever. Yeah. But anyway, but it's not the most precise now. Now the quantum clock are most precise. So this guy invented this, but he also invented this in, I think, in 78. He discovered this Huygens principle. Huygens principle, and Huygens principle, it's about waves. And what he said was that if you have some wave, right? Like, for example, maybe so-called plane wave. Plane wave means that the fronts of the wave goes like there, right? for example, wave that goes to the beach, right? Looking from above, right? So these are the peaks of the waves going like this. And when they are linear lines, it's called plane wave. Plane. Plane wave. And these lines or surfaces, they are called wave front. Wave front, if I'm not, yeah, wave front. So the wave fronts are going to the beach, right, like this. And mathematically speaking, wave front is a surface of constant phase. And this you should remember, that wavefront is the surface of constant phase. So here is phase, usually it's a peak, so the phase is 0. Here phase is 0, 2, here 2, here 2, here 2. And they are all the same here. The phase is still the same. The same thing, so the surface of constant phase. Like, for example, we may have not plane wave, but spherical wave. Like the wave that goes from that point. And it goes like this, right? All directions. Spherical wave. But again, you may talk about phase of the waves, and here phase is 0, here phase is 0, here 0, and they are 0 all on this wave front. The phase is the same. And if you look at this spherical wave in three directions, right? So it will be something like that sphere goes, right? And inside that another sphere, and another sphere, and all these spheres, like spreading, they're all wave fronts. And of course they can be very, 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 curved. But still, if you have the same phase on the whole curve, like phi 0 or phi pi or whatever, so it still have the wavefront. So now what Huygens suggested? He suggested the main principle, which is very important in physics. And he suggested, remember it in 17th century, right? He said that, like for example, we have the certain front, the wave front. For example, let it be phase equals 0, or maybe phase equals p, or maybe 2 pi or 2 pi, whatever. Now he said that each point of this wave front, actually it is spreading or inducing, right, the spherical wave in turn. Each point here, spherical wave. And the resulting, when the wavefront is going this way, the resulting is that the curve that goes like this, or surface, that goes above all these spherical waves, the superposition of all these spherical waves. And the next, again, all points on this wavefront, they create on their turn, and their turn creates another, and they form another wavefront. So this how wavefront spreads over space.
A question here.
Yeah.
How come, like in the Huygens principle, so each point, oh, I see, never mind. My question was, okay, so each one of those does create tiny little wave.
Yep.
But the resulting front is no longer a smooth curve. It goes.
No, it's superposition. If you summarize all these waves, it will be another front like this. Because sometimes they destroy each other. Sometimes they add to each other.
Okay.
Okay. And this principle, actually it allows to understand, interesting enough, it looks like simple somehow, it allows to understand lots and lots of physical phenomena. Like for example, maybe you don't know, but like if you have a wave, like plane wave of light, for example, light goes like this, right? And then you have some disk here, right? And there's usually, you know, that here is a shadow, right? So waves go, right? And there you have some screen on certain distance, some screen. Some screen. So what do you have here? Usually you have here the shade, right? But what was found in somewhere 17th century, I forgot the date, that if you have this plane wave of this one color, so-called monochromatic, and really plain, like very not spherical and everything, right in the center of the shade you will see the bright spot. So you will have like black, 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 and here is bright spot. Right in the center. And so it was not understood until physicists come to idea that that light is electromagnetic wave, not electromagnetic wave, but the wave, and it obeys this Huygens principle. What happens actually when you have a, like, for example, some hole in the wall, and the wave coming is like here, right? Hits this wall. So what happened? Here we have this wave front here, right? And this wave front you have certain points, and each of these points it generates this spherical wave according to the Huygens principle, right? So after this, so when passing here, and this thing, right? Again, it generates waves. So you have generates like this. So the light is spreading this way, this way, this way, this way, and this way. Not like in straight line, but it goes like spherical wave. It creates somehow sort of a spherical wave here after the hole. The same thing happens when you have a disk. Again, the points here, they create spherical waves which interfere with each other. Interfere means superpose. They have superpositions here, and in the center sometimes they create bright spot because they have positive superposition at this point. The same thing allowed to explain the phenomena which is called refraction. Refraction means that when light goes to some surface, right, like glass, right? So the light comes to the glass, right? When it comes here, each of these points in the wavefront, right? Again, they create spherical waves, but because the front touches this point first earlier than here, right? When this point touch here, this spherical wave is bigger than here, so we have some other angle. Antosha, you explain this, okay? Because I don't have time for this right now.
Okay.
So, and there's a refraction coefficient, so-called refraction coefficient, which is called usually n. It is like this. It's c, which is speed of light, divided by speed of light in glass, right? And the speed of light in glass is smaller than the speed of light in air or vacuum. They are different. So this can be 1 point something, right? Like for example, 1.2 or something, 1.3. So C is bigger than C glass. And then it causes refraction, change of direction of light here. So and lots of other things actually. We will talk about them next lecture, but lots of other things. Okay, Questions on this, guys? Questions?
No question.
No questions. Okay. Okay, so I have questions, guys. You have many questions now. So, but anyway, are you ready to write?
Yeah.
Okay, Antosha, it's up to you now because, you know. So, okay, there's a thing which is called double slit experiment in physics. We actually use it not using waves, but the waves, they are connected with the matter. So they're using different elementary particles like electrons, protons, molecules, whatever. So okay, so try to make it mathematically as far as possible. Okay, so you have this. You have the plane wave falling onto the wall, right? With two slits. Slits goes like this, right? Щели, короче. Знаешь, да, Антош? They're very small. So after that, the waves that are created actually totally spherical. That goes from here, right? They're totally spherical. Here it's a plane, here is spherical. And you have this length. And then here we have a screen, which actually registers falling particles or waves or whatever. Here's the screen. This is length L, capital, right? This is D, and the wavelength is lambda. Can you please create, like mathematically, try to create the pattern here, which we have from these two, with these two slits. You got the idea?
Yeah.
So it's very symmetrical. It goes like this. Nothing changed. Plane wave. Here is not spherical. They are actually they're called solenoidal. They are how it's called, cylindrical, right? You understand, right? The waves, the fronts are cylinders. Actually, it goes like this. This is the axis of cylinder. All of them are cylinders. Goes like this. CY or CI? CY, cylinders, okay. And there are some screens. So please calculate this picture. What will happen here? It's called interference pattern. Interference pattern. Interference pattern here. From these two, what will happen? Okay? This is the first question. Now, second one. Second one. You ready to write? Okay, calculate again. Calculate an angle of reflection. Refraction, sorry. Angle of refraction. If n, coefficient of refraction, is like, for example, just n. Using the principle of Huygens, of course. All of them, both this and that. So you have index of refraction and just calculate angle using this principle of superposition and Huygens, right? And you talk about this, of course, you understand, Antosh. So you have to elaborate, right? So the third is, you ready?
Yeah, I'm ready.
What do you think? That's a question of thinking. We have again this double slit experiment, right? But we have particles, right? Particles are waves, right? And we have them in this position that each particle is released some here. We hold them, right? And then release one after another. And they use this plane wave. Each particle is a plane wave. Coming, then form cylindrical wave, and then form some pattern here, right? And they remember that quantum mechanically particles are waves, the same thing. So if we release particle after particle, but only in that position that the first particle already hit the screen, and only after that we release the second particle. Then the third particle released only when the previous one hit the screen. So during the flight, only one particle exists, only one. The others are not here at all. They're not even generated. So you generate particle only when the first already hit the screen. Then you generate second, then third, and then again and again and again and again. And you have some picture here. What kind of picture would you think would it be?
So here's how you write it down. You can write down. Setup is the same as question 1. The particles of light are released one after the other.
Yeah, of light or whatever. Electrons, protons, neutrons, whatever particles. All of them are waves, so it will be the same thing for any of the particle. You can release even humans, you know, one after another. They will interfere here and do something, but you release them only when the first is already gone. It's gone, second one. Gone, second, third.
But the second particle is released only after the first one hits the wall.
So next is released only when the previous is gone already. Always.
So only after the second hits the wall.
Yeah.
Etc.
So during the flight is only one particle, only one. And what do you think the pattern will be there? What kind of? Okay. Got the question, guys?
Yes.
Okay, any other questions?
Hold on. What will be the pattern on the wall? Etc.
Oh, sorry. Okay.
What will be the pattern on the wall? Cool?
Okay.
Yeah? Okay, we're done.
Okay, guys, any questions?
Now,
Okay, think about it, calculate out. I hope that, Antosha, that you really calculate for the first thing and refraction. Try to them to use mathematics, all they can use, okay, and you can use. So try to calculate it really, what kind of thing you will have. And to think about the third question, okay?
okay.
Okay, guys, see you next time. Have fun.
Thank you, Jenna.
Okay, bye, guys.